Hello friends, so this is the third question which we are going to solve on application of Norton equivalent theorem. So we have the circuit here, so it involves two parts. First, determination of IN, then the equivalent resistance. Okay, so let us redraw the circuit, short circuiting the terminals A and B. So it is 6 milliampere. Ten kilo ohm, 30 volt. Now, when we short circuit terminal A and B, this 6 kilo ohm resistor again will go out of the question because the equivalent resistance will be 0. The shorted path has a resistance of 0. So, when we calculate the equivalent resistance, it will be 0. So, the 6 kilo ohm resistor will go out of the question when we short circuit terminal A and B. So, let us directly do that. Okay, A and B. So, 30 volt, 20 kilo ohm, 10 kilo ohm, 6 milliampere. So, we have to find this current IN flowing through this shorted path. Okay, so here let us apply nodal analysis. Let us consider this voltage here be V. This is connected to ground. So, here we have to determine IN. So, if we apply nodal equation, it will be 6 is equal to V by 10. 6 is the incoming current towards the node. This current is flowing away. This current IN is also flowing away. So, they are on the other side of the equation. V minus 0, that is ground, by 10. So, V by 10 plus V minus 30 volt by 20. Okay, that is the equation, nodal equation. So, we will solve it to find V. That implies 6 is equal to V by 10 plus V by 20 minus 30 by 20. That implies if we take the LCM, it will be 20. So, it is 6 is equal to 2V plus V minus 30. Okay, that implies 20 going on this side, it will get multiplied. So, 120 is equal to 3V minus 30. Okay, that implies V is equal to 120 plus 30 divided by 3, which is 150 by 3, which is equal to 50 volt. We have got V. IN, the Norton current, is equal to V minus 30 divided by 20. V minus 30 divided by 20. 20 kilo ohm. This is in volts. So, it is 50 minus 30 divided by 20. Okay. So, it is 20 by 20, which is equal to 1 milliampere. Okay. Volt, kilo ohm, milliampere. So, IN is equal to 1 milliampere. The Norton current is equal to 1 milliampere. We have used here nodal analysis. If you want, you can also use the mesh analysis, the KVL approach, to get the same result. You will get the same result. Okay. So, here it will be 6 minus IN. You can put the KVL equation here and we will get the same result. So, we have got the Norton's current. Now, we have to find the equivalent resistance between these 2 points. Okay. We have calculated the Norton's current, which is equal to 1 milliampere. So now we have to find the Norton equivalent resistance deactivating the independent sources. So let us redraw the circuit. So this current source, independent current source, will be open circuited. Then this voltage source, 30 volt voltage source, will be short circuited. Okay, 6 kilo ohm, 20 kilo ohm, 10 kilo ohm. So the Norton resistance, equivalent resistance, will be simply 20 and 10 are in series, they will get added up. This series combination is in parallel with 6 kilo ohms. So Rn is equal to 10 plus 20 parallel 6, which is 30 parallel 6, which is 30 into 6 by 36, which is 180 divided by 36, which is equal to 5 kilo ohm. Okay. So the Norton equivalent circuit, the Norton equivalent resistance is equal to 5 kilo ohm. We already had IN is equal to 1 milliampere. So this circuit can be represented in terms of its Norton equivalent circuit as this: 5 kilo ohm, 1 milliampere. Okay, that is the Norton equivalent circuit for this circuit here. Okay, so this is the third question related to application of Norton's theorem.